After having written all the constraints regarding the supply and demand, it's the time to write down the constraint regarding the transshipment nodes. Since we have two transshipment nodes, we will have two transshipment constraints that they are like this. The logic behind the transshipment constraints that we have two is this. The inflow to the transshipment node equals the outflow. Let's check for the first one. Here, x35 plus x36, check it, 35, 36, 37, and 38. So you see they are outflow. So I write here node 3 outflow. And here we have x13 and 23. So they are inflow to the node 3. Node 3 inflow. These two things must be equal. And it is the constraint regarding the transshipment nodes. So when you have some transshipment nodes that, of course, they don't have any supply or demand constraint associated with them, the only thing you need to consider regarding them is equality between inflow and outflow. For Kansas City, how many arrows, how many arcs do you see enter this city, enter this node 2? 1, 3, and 2, 3, as you can see here. So you write them. To check the outflow, see how many arcs, how many arrows you see getting out of the transshipment nodes. They are outflow. So we have here 35, 36, 37, and 38. Summation of these must be equal to this one. Let's check for the other one. The only other transshipment node that we have is Louisville. We have here 2 inflow, and here we have 4 outflow. As you can see from Louisville, it goes out to Detroit, Miami, Dallas, and New Orleans. And so they are 4, and we have 2 to Louisville from Denver and Atlanta. And the reason I'm reviewing it in this way, because it's very similar to the previous part. Based on the fact and the feedback on receiving from you, you should be completely good with this. Now it is done. We are done with transshipment models, and when we are done with the transshipment models, it means that you are done with section 6.1 about supply chain models. So see how much it was similar to the previous one. On one hand, we check first, we check the supply and demand, and we wrote it very similar to the previous one. And after that, we came here for Kansas City and Louisville, and the only point we need to cover about them is the equality of inflow and outflow currents with that nodes that translate, that is formalized like this: x45, x46, x47 plus x48, all the outflow, summation of the units shipped out of Louisville And here we have x14 plus x24 summation of the inflow current, summation of all the units shipped into Louisville. Louisville and Kansas City here are transit points. That's it. Okay, if you are good with everything that we discussed so far, I recommend writing the whole model yourself by checking this initial graph that we had. Because the other points that you are gonna write to get the whole model is the objective function, and you should be very good with the objective function, and it's the part that I want to put the challenge on you before I show the answer. So when you want to write the whole model, you start with the objective function. Everything is similar to the previous one. For the previous one, we had minimizing the total cost. Here it is also minimizing the total cost. You may ask, what about the cost per unit of transportation? You see, each unit you transfer from Denver to Kansas costs you $2. Each unit you transport from Denver to Louisville costs you three, and like that. Okay, try to write the whole model. You already have the decision variables. You already have the constraint. The only part you need to add to get the whole model is the objective function. So pause the model here and try to write it down yourself and enjoy your dominance on the concept. Good luck. When you finish writing the whole model, I hope you didn't forget to write the non-negativity constraint. Okay, now here it is the whole model, and this similar to the transportation problem, we have the decision variables multiplied by the cost with the associated cost, summation of all of them. After that, we have two constraints regarding the supply points, and we have two constraints regarding the transshipment nodes. Any way you are comfortable in writing the transshipment node constraint is okay. Here it is more process type of things. For example, in the previous one, we had x1 plus x2 equal x3 plus x4. Here it has made it more mathematical and more organized by moving all the variables to one side of the equation. So we have x1 plus x2 minus x3 minus x4 equal to 0. It is exactly the same thing that's happening here. And finally, you have 4 constraints regarding the destination node. And here it is the non-negativity constraint. You can take your time to check it by pausing the video. And here, now we can announce that we finished chapter 6, first section. That was supply chain model. The next one that we are gonna do in this session is assignment problem. Assignment problem is another type of network models, but I told you the network models are just similar to each other, no matter they are supply chain models, assignment problem, shortest route problem, or they are similar to each other. They are double subscripted variables, and usually you are trying to minimize or maximize something that is related to the decision variable and the associated values to each each of the variables regarding some constraints, and that's it. So we are gonna do assignment problem as the second section of chapter 6 together. Let's know assignment problems better together. With the assignment problem, assignment happens. You assign something to something else. Here, we have example of assigning jobs to machines. Okay, we have example of assigning agents to tasks, assignment of sales personnel to sales territories, contracts to bidders, and so on. In fact, we have many of assignment examples around us in real life. For example, they want to assign a letter, a mail, an envelope to a post office. For example, there are in one region, in one city, there are 2 post offices. Post office 1 and post office 2. And each of them giving service to their neighborhood. But what decides about, for example, when they get a new mail, for example, as I mentioned, an envelope, which post office, that is local post office, should get this before doing the delivery job? It's an assignment. And since there are, let's get it for the delivery part. For example, you have 3 delivery and you have 2 deliverer. Okay, you can assign it in this way, for example. So you see, you get again a network. That's the reason it is categorized in the category of distribution models, network models. In the ones that we discussed together, we have some protocols. A distinguishing feature of the assignment problem that we do is that one agent is assigned to one and only one task. To give you an example about that, to understand it better, imagine we have a class at University of Montevallo, for example, Morgan 202. Okay, Morgan 202, 8 to 9 a.m. And we have 2 professors, Professors A and Professors B. As you can see, Morgan 202, 8 to 9 a.m. is an entity. And when you want to assign professor to this one, to this class, to this time, you cannot assign 2 professor to this. It doesn't work in that way. In another example, imagine we have Morgan 202, 8 to 9, and we have Morgan 205, again, 8 to 9 a.m. You cannot assign these 2 classes to one professor. It's not possible. That's the point here. You see, when I give you a practical example, you can understand it much better. A distinguishing feature of the assignment problem is that one agent is assigned to one and only one task. No matter it is professor to class or class to professor. You cannot assign 2 professor to one class with the same time, and also you cannot assign 2 classes at the same time with one professor. And of course, all of these things are being done to an objective function that could be minimizing cost, minimizing time, or maximizing profit, that we are going to do it through the example that we are going to do together soon.